Okay, so we are discussing about sensing system. And I told you to kindly go through the discussion which we had on the mechanism of sensing system to collect the images from the ground. Okay, from the area that is in the field of view of the sensing system. So the sensing system can be operated by airborne platform. Okay, or it can be operated by satellite based platform. For our discussion, we are considering the airborne platform where the sensing system is installed with aircraft, okay, or aeroplane. So if we see the architecture, and as we have already discussed briefly in the previous lecture, where we discuss about if we see the design of sensing system, then if I discuss the various steps over here, then it's a kind of box representation. So in the first box, the component which are there, which are the part of sensing system, they are the optical component, okay. So optical component provide optical component will be given the rotation, okay. So the optics rotates to collect digital number from different picture elements along a line that I will describe in detail. Then when energy passes through the optical component, it reaches to the detectors. So in the second block, we have a detector unit. Okay. And after the detector, in the third box, we have A to D converter, analog to digital converter, plus we can say we have a storage device. So in our discussion, we will briefly explain like what is the role of these individual components. So first I consider the role of optical component with reference to the, drawing the schematic. What is how the energy is collected from the picture elements from the ground. Okay. What kind of optical mechanical rotation is provided to the optical component so that the area that is divided into the gridded cell, each cell energy coming from each cell is captured. Fine. So the first component is optical part that we consider. Okay. So as I discussed before, how sensor looks towards target area which is going to be sensed. So what sensor does? Sensor automatically divide the entire area under the observation into the gridded form. So for the discussion, I'm just drawing a schematic where a rectangular area is taken, and it is further gridded, where each grid represent ground resolution cell, and corresponding to that GRC by capturing the image by capturing the energy from individual GRC, sensing system allocate a DA number. Fine. The platform we have considered, that is airborne in this case. Okay. So airborne platform means the sensing system is mounted with the aircraft, and aircraft is moving in a particular trajectory. If I consider one trajectory over here, let's say this is the line along which aircraft is flying. Okay. And so the sensing system is downward looking. So we have a from the airborne platform, the orientation of sensors are sensor component. They are downward looking towards the ground surface. Okay, so this is a downward orientation. They are looking towards the picture element. So main part that we need to understand, like let's say if you project this trajectory on the ground, obviously this trajectory will fall let's say somewhere here. And if the sensing system has a rigid structure, it means there is no mechanical rotation. Uh, if there is no mechanical rotation, and again in the box, I draw the internal architecture of sensing system, that is detector as well as optical component. Okay. So let's say this is the detector over here, and just below the detector we have a optical system. We have a optics. Okay. And this optics, let's say if we consider one GRC, okay, so in its field of view, the energy is collected. Okay. So the energy that is going outward from this ground resolution cell, first you need to understand like how the energy is going in outward direction. If you remember the interaction, a geometrical interaction of electromagnetic radiation that is falling on the surface. Some of you is muted, unmuted. Could you please mute? Okay. So if you remember that discussion, so for the given very small area delta A, we consider a point in the delta A area that is considered as an interaction point. And as I said, as we have concluded before, for the remote sensing, we require diffuse reflection. We do not consider the specular reflection, and that will be verified over here. We consider the diffuse reflection. Why it is so? That I will explain with the discussion on sensing system part. So in the diffuse, how we can plot the direction of different energy component, incident as well as reflected. So we have an incident energy uh, that falls on the target point along a particular direction. Let's say that is having angle theta, that is oriented from normal by angle theta. If there is a diffuse reflection, then what happens? The direction which satisfies the Snell's law, in that direction you can expect most of the you can expect the highest energy component that is reflected. But even if it is diffuse, then in other direction also we will get the energy. And generally we consider the near diffuse reflectance for the remote sensing. So that in one particular direction there is no dominant component. We consider normally it is well distributed in 180-degree solid angle. If you see this envelope, so it is 180-degree solid angle. If we merge this schematic over this over here, then let's say somewhere here we have the sun. Okay. And in a particular direction, energy falls over this ground resolution cell. Now reflections take place and we have a reflected energy component in a different direction. And they are distributed in 180-degree solid angle. Fine. Let's say what happened if the surface is specular, if the surface is perfectly specular. Okay. So the if surface is very smooth, then specular reflections takes place. And in that case, what happened? Along a particular direction following the Snell's law, like if let's say from the normal at angle theta, there is an incident energy, it is reflected back in a certain direction that is oriented away from the normal direction by angle theta. What happens? Then this energy is not falling in the FOV of this detector over here. So this is the reason why like we consider the reflected component in all the direction, so that considering the source, target and sensor geometry, we do not worry about the location of from where the sensor is looking towards this ground resolution cell, this GRC. Okay, because see, even if orientation is different, but when the energy is reflected in 180-degree solid angle, then obviously the energy which that falls in IFOV, certain part of energies falls in IFOV of sensor. Okay, that is looking towards GRC for a time delta t. We call that dwell time. So this energy which is in IFOV of the sensor is collected at the optics over here, Okay. Finally, it is confined at its focus. Just see. At the focus, we have a detector, and this detector collect the entire energy that is in the FOV, IFOV of this sensor, this optical part over here. This is the optical part. Okay. Now next to the optical, we have a detector, and after the detector, as I discussed over here in the to the block diagram. So first is optical component, then we have a detector, and third part, uh, when detector generate the voltages, then those voltages are converted by A to D conversion. They are converted into discrete numbers following the decimal number system. We call them digital number. Okay, and they stored on the device. So this is the last stage. Now see, our objective is not to, if let's say this aircraft is moving along its trajectory, and if we project trajectory on the ground, so that trajectory is along the line, that trajectory is along a line on the ground, but our aim is to cover the entire area, not a particular line in one when the aircraft is moving along a fixed trajectory. We want to cover this entire area across the trajectory. If the optical component is not rotating, they are fixed. Okay, then what happens? If they are fixed, it means only the GRC which are along this trajectory, energy from them are only sensed. Okay, but our aim is to cover the entire strip across the trajectory. So like, if I further draw a figure representing a different nomenclature over here, then it will be easy for you. So in our discussion, we have discussed about flight line. We also call it trajectory. So this is the flight line along which aircraft is flying. Okay, and this flight line also tells you the location of sensor that is installed with moving platform. Now across the flight line, we have an area strip. Let's say one area strip, then what is our aim? Our aim is to map an entire strip in one flight line. Entire strip means a certain width across the flight line. So this is the width that should be mapped in the sense like from the ground resolution cells, energies needs to be collected. So across the flight line, how much width can be covered? It depends on what kind of provision we are providing over here. What kind of rotation provision we are providing at the optical component. Okay. If we do not have any rotation, if do not provide any rotation to the optical component, what will happen? Only along the flight line, the information of ground resolution cells are collected. Just see over here. Okay. Reason is that this is the downward looking sensor. Okay, it is just looking below. If a rotation is not provided, it is just looking below the trajectory. We call it nadir direction. See, in this diagram, just consider this is as a normal direction, normal from the surface. Because I have drawn the figure in oblique view. So this is the normal direction. Okay. Can anyone suggest me like what kind of provisions should be given to the optical component so that rather than acquiring a single pixel, rather than sensing the single GRC across the flight line, we can cover at least certain extent, certain area can be covered. So what kind of provision we need to provide over here at the optical component? What could be the possibility?
Sir, we can give some kind of rotation kind of thing so that it can cover some extent like fib angle like 120 degree till or 130 degree in cross width of flight line.
Fine, that part we already discussed in the previous lecture. Like part of discussion we have already done. Can we provide any other provision? Can we apply any other modification to which we can do this?
So like in across scanners, the cameras and optical instruments are installed in the sideways of the aircraft. Then they can sense the sideways path which are left just because of downward looking sensors.
No, that is one part. Like providing the rotation to the optics, at least we can swipe. Okay, we can swipe across the flight line to cover a certain extent of area. Fine. Could we provide any other modification to the sensing system where it can be achieved? See, our objective is not to capture only a GRC below the flight line, as I have drawn over here. Our aim is to cover across the flight line the certain area. We call it just a strip. Okay, a complete area strip we want to capture in a one flight line. So just I would like to discuss with you. Fine, like optical part we have by providing the rotation. I will explain it by providing the rotation. How we capture the energy from different GRC which are connected across the flight line. Like I'm talking about these GRCs which are connected across the flight line. Okay, see, I will explain over here how it can be done. This is the detector. We call it CCD, charge coupled device. Okay, 1 unit of CCD. Then Let me rewrite again. So when you project a flight line on the ground surface, it will fall over here. Let's say it passes along the GRC which are connected along the flight line. If there is no rotation in the optics, then what happened? As I discuss over here, the GRC which are connected along the flight line, only energy from those GRC was collected. Fine. But if we provide a rotation to the optics means we have a mirror over here. This is its normal direction. Okay. Now, if you change the normal, if you rotate it, so initially, let's say it focuses to this GRC. After providing the rotation, now it is focusing to the next ground resolution cell. Okay. Similarly, if you provide again, so it can be either rotated or oscillated. So mirror could be either rotating mirror or oscillating mirror. Fine. So in this way, the ground resolution cells which are confined within the two extremes, left side leftward and rightward, by providing the rotation to the optics with reference to the um, time, what happens? Energy from different ground resolution cells which are connected across the flight line direction. They are connected across the flight line direction. They are required. But is this the architecture? No. What happens if you provide a rotation over here? At the same time, the platform also moves forward. Okay. So the way pixels the pixels informations are captured, okay, it is not perfectly across the flight line. It will be in the slant direction. Like let's say if the first pixel is acquired from here somewhere, let's say if I consider, okay, now there is a movement, and after the movement, what happens? Let's say delta d distance, the flight moves forward. So second pixel will be this. Now the third pixel will be this. And if we consider the in cross the flight line within the two extremes, which are separated by width W. Okay, this is the pattern in which the pixels energies are collected. Fine. So okay, in this way, what happens by providing this modification, by providing this rotation? Now, instead of only capturing the GRC along the flight line, now we can collect GRC across the flight line covering the width W. And now this will be the area, entire area strip of width W, for which uh, we can collect the energy from ground resolution cells. Okay. But see, if we consider the level of complexity in system, so the first part, this is the mechanically rotating system. It is a kind of complex system. Due to and it is due to providing the rotation to the entire assembly. So to cover the width W. Fine. And the way the pixels are acquired, okay, we name it a Wisp-Boom scanning system. This is a scanning system, and the way the pixels are collected, like it is providing the rotation to the optics, and adjacent pixels are adjacent ground resolution cells are being sensed. Okay, we call it a Wisp-Boom scanning system. Wisp-Boom scanning system. So it is a kind of booming where like you swipe from one end to another end. Okay, so that is the reason why it is called as Wisp-Boom scanning system. By rotating the optics from one end, from where the system is initialized, it is going to another end, and energies are collected. Few things you need to consider over here while swiping from one end to another end. This optics this mirror looks to a particular ground resolution cell for time delta t. Okay, and we call it a dwell time. This you need to remember. We call it dwell time. So for delta t time, one ground resolution cell is sensed by the from one ground resolution cell for delta t time, energy is collected at the optics at the mirror over here. And finally, it is confined to the CCD. So CCD, one charge coupled device, is sensing one ground resolution cell for time delta t. And it is sensing the energy that is in FOV, that is in IFOV of, let's say, if consider this IFOV of optics. Okay. So if we consider like let's say if we consider total time that is taken by the system to capture the information of all the CCDs which are connected across the flight line. Let's say if there is total n number of CCDs, this is n to n number of ground resolution cell from 1 to n. So by n number of ground resolution cells, that we consider the across the flight line. Okay, total time that is taken by the sensing system is t. To sense them, the time taken by the sensing system is t. Then time taken, that is delta t, I call it dwell time, it will be capital T divided by n. Okay. What happens if we want to sense this area without using this optical system? What modifications should be done? Let's say if we remove this optical system, there is a way through which we can do it. We can remove this optical system. Okay. And we can increase the CCD from 1 to n number of CCD. All these sensors are these CCD optical system, they are downward looking. Now what we do, laterally we increase the CCD. In the previous case, there is only one CCD. Now we cascade them. So in the cascaded modified version, we have a many CCDs connected in series. Okay. Now when you initialize the system in their own FOV, now we don't have any optical system. Just the CCDs are looking towards the ground resolution cell. So this is in IFOV of first CCD. If we start naming from right hand side, so this is the first CCD. Its second CCD, it's field of view for the adjacent ground resolution cell. Then by the third, fourth, like that. What is the benefit of this modification over the previous case?
Sir,
So,
one question is there, sir.
mm-hmm.
Sir, is it the situation that each CCD considers or takes the radiations only from one particular GRC at one time?
Yeah, it is the case. But see,
Oh.
uh, uh, if we see in a practical case, okay. So though we say that we define a ground resolution cell over here on the ground on the basis of geometry of a CCD, okay. And when once the energy is reflected back from the GRC, we consider the spread of that energy within the atmosphere. By considering all the factors, we decide the spatial resolution. Because when I say CCD, when I say ground resolution cell, so the dimension of GRC is determined by its shape and size. Fine. Shape, if we consider the square, then size M represent the spatial resolution. So this spatial resolution is determined by the geometry of a CCD. And also we consider the atmospheric factor. Fine. So if you project this trajectory over the ground, across the trajectory we see like what is the FOV. If we see like how much area can be from how much area energy can be sensed by the one CCD. Similarly, in the adjacent case, there may be some overlap. Okay, but what we consider like this CCD is uniquely sensing the adjacent ground resolution cell, but it is not practically, it is not possible. Some part of energy from the adjacent area, adjacent GRC also falls in the within the CCD2 due to spread of energy in the atmosphere. Fine. Even in the third case, but what we consider the while the analysis, one CCD sense one GRC. Okay. The adjacent CCD sends the next GRC. In this way, across the flight line, width is covered. And we say it like strip of the area is acquired in one flight line. And the width of that area is computed on the basis of how many CCDs we have in this cascaded version of architecture, where the CCDs are connected in series. Fine. What is the benefit of this kind of architecture over the previous case? One more thing, like what is the nomenclature of this type of sensing system? If you see the way data is acquired, it is kind of pushing the cascaded CCDs along the flight line. So here you can't notice like these are they are acquired like this. GRCs are acquired like in a slant direction, not perfectly perpendicular to the flight line. While in this case, ground resolution cells are acquired across the flight line, in the direction across the flight line. While in the first case, the direction is not completely perpendicular, it is slant, somewhere tilted from the perpendicular direction of flight line. Okay. Can anyone tell me what is the benefit of okay, the way I was talking about the architecture, the mechanism, the way the area is scanned. So it is kind of pushing the entire system in a forward direction towards the flight line. This is the reason why we call it push boom. Again, it's kind of booming, just cleaning the entire area. Cleaning means just collecting the energy from different GRC. It is like once you collect the energy from ground, from different GRC, it is cleaned. This is that is the reason why we select a terminology booming. So it's a push boom scanning system. It's not kind of whisk. Whisk means like swiping from one end to another end. That was a case in the sensing system we discussed previously. In this case, there is no swiping from one end to another end. We don't have any optical system over here. We have only charge coupled devices connected in series, and they are pushing forward along with the movement of aircraft. And just sensing the ground resolution cells, which are just in their FOV below the ground. Below the aircraft and from the ground. So we have seen that like from where we have started. We have started with discussing the major components which are the part of sensing system. So there I said that while the discussion, we have optical component, detector, then we have electronic components which convert voltages which are generated by the detectors into a data format that can be stored on the storage device. So our ultimate goal is to generate a data format that is compatible, that can be stored on the storage device. So A to D converter, then further how the decimal number system can be converted into the binary number system for storage purpose. We have already discussed. So this part we have already discussed previously. Okay, and in today's discussion, we have also completed this part, the first two part. So with reference to these block diagrams, we have two types of scanning system. So type of scanning system is determined on the basis of these sections. Okay. Now the remaining sections are common in both the cases. The arrangement of different components in optical system as well as the detector part, we categorize the scanning system into two categories. The first one is a wishbone scanning, where we have optical component and detector. Fine. What is a we have an optical component, we have single detector. But we like to cover a certain extent of area across the flight line. When you project that trajectory over the ground, as I discussed over here, you need to rotate the optics, okay, so that it can swipe from one end to another end to look at different GRCs. So one detector is looking at a different GRC across the flight line in a subsequent time interval. And the GRC, this detector looks at a particular GRC for time delta t. If total time taken by the detectors, the entire sensing system, the first two part, to sense the GRCs which are connected across the flight line, if the time is total time is t, then dwell time, that is time taken by sensing system to sense the energy coming from one GRC is t divided by n. N talks about how many GRC we have across the flight line. Fine. Considering the second case where we don't have an optical component, so this optical component is not there. We cross it. We have only detector, not single detector. We have a multiple detector. If I write over here, wishbone system and just see the difference. We have an optical component and detector we have single. We don't have optical component, we have a multiple detector. Multiple detectors. It's better to write CCD. Multiple CCDs connected in series. Now we'll see what is the benefit in terms of data quality. That is most important part. To get a better data quality, how we define data quality? Data quality we define in terms of certain resolutions. The first one, what is the spatial resolution we get? So that spatial resolution talks about the size of GRC. We prefer data quality is better if we prefer the smaller GRC. Similarly, we talk about spectral resolution, we talk about radiometric resolution. So these three parameters, spectral, spatial, and radiometric, they are used to characterize the quality of image. Our next discussion will be on these resolutions part, and we will see how the data quality is affected by changing these resolutions. Okay. But certain concept we establish over here in the context of wishbone scanning system and wishbone scanning system. We'll see what is the benefit of wishbone over wishbone. Now the total time delta t the total time delta t that is taken by the sensing system to scan the GRC which are across the flight line, nearly the same time delta t is taken by the CCDs in push-pull scanning to sense the individual GRC. I hope you are getting my point. In case of push-pull scanning, delta t is the total time that is required to scan all the GRCs across the flight line. Fine. That provision is given. That all depends on the speed of moving platform. Okay. And in the first case, it also depends on the speed of rotation, angular speed of rotating mirror. So if in the both cases, if aircraft is flying at same speed v, if we consider the first case, then in one rotation from the first end to last second end, between the two extremes, the time taken is t, but this time t is divided by n to estimate how much time is taken, how much time is allocated to sense one GRC. Because for only delta t time, the optics is looking to one GRC. Now it rotates further and now it goes to the second GRC. While in this case, there is no rotating part. All the CCDs are looking at their respective GRCs for the entire time delta t. Okay, what does this mean? It means more energy is collected from a CCD in case of post-boom scanning compared to the vis-boom scanning. Because in vis-boom scanning, a very less time is allocated to sense one GRC. That is delta t, that is t divided by n. While in case of post-boom scanning, the entire t time is allocated to sense one GRC. So if sensing time is more, it means more energy is collected from that GRC. So if more energy is collected, it means the image quality will be better. Okay. Now, how it can be quantified using mathematics? I will discuss with you a mathematical formula that estimate how much energy is collected from one ground from a GRC for the allocated dwell time from the given dimension of GRC that is defined in terms of spatial resolution M. And finally, if we see the detector part over here, so detector sense the energy only within a spectral band in which that CCD is designed. Okay, so energy is also measured spectrally. Like what is a range of wavelength? Okay, within which the energy is being sensed from the GRC. What does this mean? I hope one more diagram I plot over here. If there is any doubt related to type of scanning system on the basis of architecture of data acquisition, okay, then you can discuss that part if there is any query related to that.
Sir, means you are saying that in push broom scanner, at one time more number of GRCs are radiating, more number of energy is getting to the push broom scanner. That is why quality will be reduced as compared to whisk broom scanner.
Mm-hmm.
Okay, sir. That is I was confirming it. Then, sir.
Yeah, and further na, through a mathematical formula, we'll see how it happens. Okay,
Okay, sir.
that part I'm going to discuss how we can combine the effect of spatial resolution, effect of dwell time, as well as the bandwidth of the given spectral band, how they affect the total energy collected at the sensor. Okay, because see, ultimately quality of image depends on what is the amplitude, what is total energy that is collected at the sensor. We'll see it. Okay, so what I'm talking about in the context of entire discussion, okay, related to the sensing system, what we have seen, we are discussing about a ground resolution cell very frequently, that is GRC. This is one of the important component. For the given GRC, we collect the energy, we assign a DN number. Fine. So one GRC, finally in the output, you have a digital number. So GRC is characterized by its shape and size. We consider is square. It has size M. So M is termed as spatial resolution. Fine. Now what happens if it is sensed by one CCD? For the simplicity, I do not consider a mechanical this optics part over here. Let's say this energy outgoing energy from a GRC is collected. When the incident energy, when the energy falls on a particular GRC that is having area M square. Okay. So from each point, there is a reflected energy component. What does this mean? It means the each point on the area, total area M square, they have their contribution in the total outgoing energy. Okay. It means if you increase the area, what will happen? The total outgoing energy will increase because now there are more number of interaction points. Now it is clear over here, by increasing M square, the total outgoing energy from the target is increasing. Fine. Now the second part, I talk about this CCD is looking at this particular GRC for time t. It means for time t, the photons which are coming out, because in the energy we have the photons. So specific energy is being collected within time delta t, that is constituted by photons. If you increase time t, then you collect more number of photons from the given area A. Okay, so what does this mean? If sensing time, that is called as dwell time, if this dwell time increases, it means more amount of energy now collected at the sensor. Now see, I'm talking ES. Due to increase in GRC, energy reflected from the target is increasing. That's why I've written ET. Now by increasing the dwell time dt, energy sensed at the CCD ES, it increases. Fine. So what happens? Now I draw wavelength axis over here. As I told before, in multispectral sensors or hyperspectral sensors, the sensing system that is comprised of CCD is sensitive in a certain spectral band. So let's say if we see over here, this is the visible spectrum, 0.4 to 0.7. Then we have a NIR. Then we have a MIR, mid-infrared, far infrared, microbit, etc. Let's say this CCD is sensitive somewhere here. Okay. This CCD is sensitive somewhere here in an IR band. So this is the spectral band. Let's say it's B4. So this CCD is corresponding spectral band B4. Okay. Now see the energy ES that is reaches at the sensor has the energy component in all the available wavelengths. Obviously within the atmospheric windows. So within the atmospheric windows, the energy ES is available at the sensor. But what actually CCD is doing? CCD has a kind of filter. That filter only filter out energy where CCD is sensitive. And let's say it is for band B4 and it is in an IR band. So let's say we have a range. The B4 range that I'm talking about, it is lambda 1 to lambda 2. Now see what happens if lambda 1 to lambda 2, if we take the difference between these two, let's say this is delta lambda. Delta lambda is lambda 2 minus lambda 1. Okay. So lambda 2 minus lambda 1, it's delta lambda. Delta lambda is actually bandwidth of this band B4. Now tell me what happens if you increase the bandwidth in terms of total photons which are collected at the CCD. Or in other way, the magnitude of energy ES. Again, it is ES at the sensor. Now it will be ES4. ES4 is a subset of ES, and it is only within the band B4. So if for this specific band B4, if you increase delta lambda, then what will happen with the magnitude of energy ES4? Abhijit Sonkar, could you please unmute? Abhijit,
Yes, sir.
could you tell me, uh, like when we increase the delta lambda, that is a difference between lambda 2 minus lambda 1 over here. We can also say it a bandwidth for band B4. If you increase it, then magnitude of ES4 will decrease or increase. How many of you know this, the explanation for this? Kindly raise your hand. You can mute yourself. Please raise your hand. How many of you know the explanation for this query?